All right, we are going to be dealing with stoichiometry problems. We're going to do simple mole-to-mole calculations and then get into a mass-to-mass calculation. So this top box is just basically what our textbook shares with us, that a balanced equation allows us, if we know the moles of one substance, to then be able to tell you the moles of another, whether it's a reactant or a product. In that balanced chemical equation, those substances are stoichiometrically equivalent to each other, which means that, again, if we have a specific amount of one substance that's formed from, produces, or reacts with a specific amount of another, and we can use that relationship from that balanced equation and their coefficients. This goes right along with our AP objectives in the sense of those coefficients in our balanced chemical equations provide the proportionality of the amounts of substances involved. So in this first one, if we're looking at our first balanced equation, this is telling us that for every 3 moles of magnesium chloride that react with 2 moles of aluminum, we will make 3 moles of magnesium and 2 moles of aluminum chloride. So this is the relationship between them. And we can use this in dimensional analysis because, let's say, for every 3 moles of magnesium chloride, I know it's with everything else, like aluminum in excess, I am going to get 2 moles of aluminum chloride. So let's look at just some basic calculations with this. So this is saying we have 8 moles of magnesium chloride that react with enough aluminum. How many moles of aluminum chloride are produced? So we're going to start with our given, our 8 moles of MgCl2. And this is where labeling stuff and staying super organized is going to be really important. We have started with moles of magnesium chloride. So I'm going to put my moles of magnesium chloride down here. And in this, we're saying that we are going to use that balanced equation to relate 2 equivalent pieces in this reaction. So up here, I'm going to use my coefficients. So for every 3 moles of magnesium chloride, I am going to produce 2 moles of the aluminum chloride. Okay, and again, those are just coefficients. Okay, but I can use those as 2 equivalent pieces based on the given reaction. Okay, and then from there, I'm in my moles of aluminum chloride, which is what I'm looking for. So if you multiply across the top, divide by the bottom, keeping to my 2 sig figs that I started with, you'll have 5.3 moles of your aluminum chloride. So if I have 8 moles of magnesium chloride with enough aluminum, it will produce 5.3 moles of my aluminum chloride. Okay, feel free to pause and try out the next one and then check back in. So with this one, it's saying that we have 10 moles of aluminum. How many moles of magnesium chloride do I have? So I'm going to start with my 10 mole of aluminum. Okay, my given amount. This is the pure aluminum. So when I come up here to my balanced equation, this is showing me that for every 2 moles of aluminum, and we're looking for magnesium chloride, it will react with 3 moles of the magnesium chloride. All right, and then if we have 10 times 3 divided by 2, it's going to be 15. Okay, and the 3 sig figs that I start with, I have to make sure I put the 0.0 here so that I have my 15 moles of magnesium chloride. Okay, so this is just using that relationship of our equation to go from moles of one thing to moles of another. But we know that in the lab, we're not measuring in moles, we're measuring in grams. So we're going to be doing like a mass to mass conversion here. Well, we'll start with the mass of one reaction or product. Okay, we'll get moles of that reaction or product. Then we'll be able to use that mole to mole conversion to get moles of our new reaction or product and then move to mass. You'll also see an example in the practice where we involve the molar volume if we have a gas at STP, so you may see that as well. All right, so let's get to a mass-to-mass calculation, which is really what we're going to be using a lot of this year in chemistry. So with this first reaction, you're going to see that we have 1 mole of nitrogen reacting with 3 moles of hydrogen, produce 2 moles of ammonia. So this is the relationship within this reaction that we can then use in our dimensional analysis and perform stoichiometry. So in this question, we have how many grams of hydrogen, and hydrogen is talking about H2 up here, the pure hydrogen, are needed to react with 56 grams of nitrogen. And here we're talking about the pure nitrogen up in the reaction, which is N2. And that just becomes important when we go to do molar masses. So I'm going to start here with my 56 grams of N2. So that first step is just getting this into moles so that we can use the reaction and the moles in the reaction. So here I'm using my molar mass, which using the AP reference tables and adding that up, you get 28.02 grams of N2, and that's equivalent to 1 mole of N2. Just remember at this spot where you're using the molar mass, those grams are always equivalent to 1 mole. It does not matter what their coefficients are up top. When those coefficients do come in is when we switch from moles of N2 to moles of H2. So I started with moles of N2. So I'm going to place those down here. I'm looking to go to moles of H2. Okay, our coefficient of 1 for N2 is then going to go with my moles of N2. 1 mole of N2 will react with 3 moles of H2. And that completes that step of our dimensional analysis. Now that I'm in moles of H2, I want to get back to grams because that's the mass I'm interested in. Just make sure here that this grams, 2.016 grams of H2, is always equivalent to 1 mole of H2. Remember, these have to be equal to each other. It doesn't matter that we had 3 moles up here. Okay, that's already taken care of in this step. Okay, and then that is our setup, going from grams of N2 to grams of H2. So we go and plug that in, and keeping the 4 sig figs, you should get 12.09 grams of H2. Okay. All right, we're going to then do this next one. We're dealing with H2 and ammonia. So here it's saying we have 36 grams of H2. How many grams of NH3 are going to be produced from those 36 grams of H2? And this would be under the assumption that you have as much nitrogen available to react with those 36 grams of H2. So I'm going to start with my 36 grams of H2. Okay, and again, I want to get 2 moles so that I can use the mole relationship in the reaction. So this would be the molar mass of 2.016 grams of H2. That molar mass is always equivalent to 1 mole of the substance. Okay, in this next step, then I'm going to be able to go from H2 to NH3, which is what I'm interested in. So I'm starting with moles of H2. Okay, so I need to make sure that's in the denominator. I'm then up top here going to have moles of what I'm looking for, which is NH3. Okay, then I'm going to plug in based on their coefficients up here. So for every 3 moles of H2, I'm going to produce 2 moles of NH3. So I can place that there. Okay, and then my last step, I want to get this into the unit that I'm looking for, which happens to be grams. So this would be my 1 mole of NH3. Its molar mass is 17.03 NH3. And again, remember that molar mass is always equivalent to just 1 mole. It doesn't matter what it is in the reaction. These two things have to be equal to each other. And then when you go and plug that in, keeping the 4 sig figs that we started with, you should get 202.7 grams of NH3. All right, let me just show you one with volume, just because it might have been a while since you've seen molar volume. So here it's talking about what is the total volume of CO2 formed when 6 liters of ethene are completely combusted. And we can see the reaction up here. So here we're starting with liters. And if you remember back, we did talk about how if a gas is at STP, 22.4 liters of that gas at STP is equivalent to 1 mole of its, in this case, molecules. Okay, so here we're not involving grams because we're starting with liters. But once you get it into moles, we can still use the relationship from the formula. So for every 2 moles of ethane that we consume, we're going to get 4 moles of CO2. So just be careful. Make sure you start with the 2 moles of C2H6 down below here, and then it's going to produce the 4 mole of CO2. And then here they could ask for grams, but they're asking for volume. So because this is also a gas at STP, we know that for every 1 mole of that gas at STP, it will be equivalent to 22.4 liters of that gas. And then just keeping to the 2 sig figs that we started with, you will get 12 liters of CO2. And I usually like to note that that's a gas at STP. All right, so that is it. Just basically building off of what we did in the previous lessons and adding in this mole relationship that the equation gives us.